In this video, I would like to talk to you about properties of probability. Let's consider a probability law P and let A, B, C be events. I'm going to talk to you about 4 properties and I'm going to prove each one of them. I know the name proof sounds scary, but don't worry, the proof that I'm going to give you, they're easy to understand and they're cute because I'm going to use Venn diagram for each one of them. So let me start by bringing up the probability axioms. So the first one, if A is a subset of B, then probability of A is less than or equal to probability of B. Let me start by graphing a Venn diagram in here. So this is our sample space omega. I have the set B and I have the set A. Inside B is just because A is a subset of B. Then, as you see, I can write B as what? As A. So A is here. And look at this part in here. This part is actually B intersection with AC, and the union of these two sets is B. So I can write B as the set A and union of B intersection with AC, which means that all the elements of B that are not in A. Okay, so as you see, these two sets are disjoint, the set A and the set of elements of B that are not in A. These two are disjoint, so based on the third axioms, if I have 2 disjoint sets, the probability of their union is the addition of their probabilities. So by axiom 3, probability of B is probability of A plus probability of B intersection with AC. Okay, probability of any event is a positive number by axiom 1. Okay, so this is a positive number. So probability of B is probability of A plus something positive, which means that probability of B is greater than probability of A. Okay, so this part in here, probability of A plus probability of B intersection with AC is greater than or equal to probability of A, because this thing in here based on the axiom 1 is something positive and a positive number. So probability of B is greater than or equal to probability of A. Great, this is the first one. So let's go to the second one. Okay, probability of A union B is probability of A plus probability of B minus probability of their intersection. Okay, so let me have 2 Venn diagrams actually here. One, this is the second one, okay? And I have this set A, I have the set B, and the same thing. I have the set A, I have the set B. Okay, the same thing, but I wrote it twice. So look at this one. Probability of A union B. A union B is basically everything. Okay. So I can write A union B as what? I can write this as A, the whole A is here. Okay. A, and I take the union of A with this part. This part in here is what? This part in here is B intersection with AC. Elements of B that are not in A. So this is the purple area. So A union B is the union of two disjoint sets, as you see here. So based on axiom 3, if we have two disjoint sets, the probabilities would be their summation. So probability of B union A is probability of A plus probability of B intersection with AC. Okay. Now, I would like to talk about the probability of B here. So I can write B as what? As this little area, which is A intersection with B, and I take the union of that with, let me use the purple, so with this area. This area would be B intersection with AC. Okay, so I wrote B as two disjoint sets. One is the blue area, which is A intersection with B. The other one is purple area, which is B intersection with AC. So I have two disjoint sets again. By axiom 3, probability of B is probability of first one plus probability of the second one. Now I have two equations in here. Okay, so I'm gonna subtract them. How? I'm gonna multiply the second one by a negative sign, and I'm gonna add them up. So this minus that, let me write with this color. So probability of A union B minus probability of B is equal to the right hand side is probability of A plus probability of this set minus probability of A intersection with B minus this set. So these two would be cancelled. This and that would be cancelled. So I get probability of A minus probability of A intersection with B. Okay, so this equation in here, if I bring a negative probability of B on the other side, would be exactly this one. So how did I prove this? I wrote A union B as two disjoint sets, A and B intersection of with AC, and I wrote the set B as this blue area with this purple area, and then I subtract them, and that's how I basically erase the term that I didn't want, B intersection with AC, and I got this equation. Great. How about the next one? Probability of A union B is less than probability of A plus probability of B. This is obvious based on part B. Why? It's just because, as you see, probability of A minus B is probability of A plus probability of B minus something positive. So this part in here is greater than this part because P of A union B is this number minus a positive number. Okay, so basically I subtract something from A minus B to get that. So this equation is based on this part. Great. How about the last one? The last one seems kind of too many information, but it's not that much hard. Let me have the Venn diagram in here. Let me have 3 circles, 1, and then let me have 2. Let me have another one, and let me have the third one. Great. So let's have one of them to be A, one set A, one set B, one set C, and this is the whole sample space, omega. So probability of A union B union C. If I can write this A union B union C as some disjoint sets, then I'm gonna use the third axioms and I'm gonna just get the result that I want. So I'm gonna write A union B union C as the set A. You see, the set A would be here. Okay. And then I'm gonna include this one, which is, so this is A. This is A. This is all the elements of B that are not in A. So it would be B intersection with AC. And I'm gonna have the last part. The blue part is what? All the elements of C that are not in A and they are not in B. Great. So I wrote the union of three events as three disjoint unions, and so based on the third axiom, I can add them up. We would like to solve this example. In a survey of 120 adults, 55 said they had an egg for breakfast that morning, 40 said they had juice for breakfast, and 70 said they had an egg or juice for breakfast. How many had an egg but no juice for breakfast? How many had neither an egg nor juice for breakfast? Okay, to understand the problem, it's better to graph a Venn diagram. Okay, so this is U, which would be the universal set. I have a set E, and E is the set of all people that had egg for breakfast. So people who had egg, just had an egg for breakfast. Then we have another set, J. Let me just move it just a little bit. So J, this is the set of people who had juice for breakfast. Okay, and so what do we want is we want to see how many people do we have in each of these sets. So let's see what information we know. N of E, okay, and what is N? N stands for the number of elements in set E, for example. So NE, the number of people who had egg, is 55. Then N of J would be the number of people who had juice, would be 40. Then we have N of 70 is the number of people who had egg or juice. Whenever that we see or, it means union. So N of E union J is 70. What else do we know? Nothing else for now. And let me do something else. I'm gonna say that I have X people in here. I have Y people in their intersection. I have Z people in J, and I have W on the outside. Okay, very good. So based on whatever that I wrote over there for X, Y, and Z, N of E, which is 55, would be X plus Y. Okay, E contains both X and Y. And J would be Y plus Z. N of E union J would be X plus Y plus Z. And now something else I know. I know one other equation that is x plus y plus z plus w is 120. So x plus y plus z plus w is 120. Okay? So now let's figure out x, y, and z. Okay? Let me start by something very kind of small. I'm gonna start with y. Okay? I want to figure out what y is. So y is n of E intersection with J, right? So if you remember union rule for the set theory, E union J is E, N of E union J is N of E plus N of J minus N of E intersection with J. So this is something that I want to know. N of E is 55, N of J is 40, and N of E union J is 70. Okay, so this is 95 in here, 70 in here, and so I get N E intersection with J, basically the number of elements in the E intersection with J is equal to 95 minus 70, which is equal to 25. So I have 25 elements in here. So y is equal to 25. Very good. Now look at all the equations that I have in here. I have y equals to 25. So since x plus y equals to 55, y is 25, therefore x would be 55 minus 25, so x is 30. So x is 30. So I have 30 people in here, in just this area. I have 25 here in their intersection, and I have 25 in here. So based on this equation, I have z equals to 40 minus 25. This is 15. So I have 15 people in just J. Okay. And so this is 70. I know x plus y plus z is 70. You can check that the numbers that you got are correct. And look at here, x plus y plus z, this is 70. And based on that, w is equal to 120 minus 70, which is 50. So this is 50. If I want to interpret x, y, z, and w, I can say x is just, as you see, is just the number of people who just had egg. Nothing else, not juice. 25 people had egg and they had juice. 15 people, they just had juice, and 50 people, they didn't have anything. No egg and no juice, right? Okay, now that I got all these numbers, go back to the question. How many had an egg but no juice? So if I want to interpret this one, what should I write? They had an egg, so E, but no juice. But no juice means that and means intersection. They had no juice. Okay, let's see where this set is. It's E in here. Let me highlight it. E intersection with JC. It means that all the elements of E that they are not in J. So this area in here. Okay. So N of E intersection with JC, which gives us the number of people who had egg but no juice, is X, and it's equal to 30. That's what we got. How many had neither an egg nor juice? What does this one mean? They had no egg nor juice. It means that they had no egg and they had no juice. It's this. EC intersection with JC. What is this? If you remember the De Morgan's law, let me just give you just a small recall of De Morgan's law. It's A intersection with B complement is AC, A complement union B complement. And also backward, A complement intersection with B complement is A union B complement. Okay, so that I have the complement of two sets. Okay, it would be E union J complement. Okay, this is based on the De Morgan's law. Now that I want to find the number of elements that are in both, let's see what E union J complement, where is this one? E union J is this set, is the whole setting here. This is E union J, right? Now that I want to see the complement of that, the complement would be exactly everywhere in here. Okay, so the number of elements or people who had no juice and no egg would be W, which is equal to 50. In this example, we're going to see how to use probability laws to solve a question. A company has bids on 2 contracts. They believe that the probability of obtaining the first contract is 0.4 and of obtaining the second contract is 0.3, while the probability of obtaining both contracts is 0.1. Find the probability that they will obtain exactly one of the contracts. Find the probability that they will obtain neither of the contracts. So whenever we have this kind of a problem, it's good to have a Venn diagram. So let me start by a good Venn diagram. So I have a set, let me call it F, and F is the event of obtaining first contract. Let me have S to be the event of obtaining the second contract. Okay, so what do we know? We know that probability of F is 0.4. We know that probability of S is 0.3. And we know that the probability of their intersection, F intersection with S, is 0.1. So let me just write 0.1 in here because this is something that we know. Great. We want to find the probability that they will obtain exactly one of the contracts. So what does that mean? It means that obtain exactly one contract, they may obtain the first contract but not the second one, or they may obtain the second contract but not the first one. Great. So in terms of F and S, the first contract would be F, but not, it means that, and not the second one. S complement. Okay, this is the first contract and not the second contract. Okay, and we have an or in terms of the set theory means the union, and then second contract, which would be S but not first contract, would be and F C. Okay, so where are they in the Venn diagram? F intersection with SC is here. All the elements of F that are not in S is here. Okay, and S intersection with FC would be all the elements of S that are not in F would be here. As you see that these two sets are disjoint. So whenever that we have a disjoint events or mutually exclusive events, we can add their probabilities. So something that we want is probability of F intersection with SC plus probability of S intersection with FC. This is probability of exactly one contract. Okay, now let's find these two. Okay, looking at the information that we have probability of F is 0.4. Okay, so probability of F, since, so you see the set F is equal to the intersection, just here. Okay, so let me write it. So F is F intersection with S, this part, okay, union with that part, union with F intersection with SC. Okay, so since these two are mutually exclusive, since these two are disjoint, I can write probability of F as their summation. So it would be, their summation would be the intersection 0.1 plus probability of the blue area, F intersection with SC. Therefore, the probability that I'm looking for, F intersection with SC, is 0.4 minus 0.1, which is 0.3. Good. How about the second one? The second one, for probability of S, I have the same thing. Probability of S is the probability of the intersection union with the probability of this pink area, which is S intersection with FC. Okay, and so since these two are disjoint, I can write this as 0.1 plus probability of S intersection with FC. So probability of S intersection with FC is equal to 0.3 minus 0.1. So this is 0.2. Great, I found these two sets, so I can plug it in here. Probability of F intersection with SC is 0.3 plus probability of S intersection with FC is 0.2. So together I get 0.5. Perfect. Second question. Find the probability that they will obtain neither of the contracts. Okay, what does this one mean? This one, neither of them, it means that it's F union S. F union S means at least one of the contracts, right? It means that you get the first contract or you get the second contract. It means you get at least one of them. Then I get the complement of that to find the event that neither of the contract is my target. So probability of that is equal to what? Let me write this. So probability of neither contracts is equal to probability of F union S complement, which is 1 minus probability of F union S, right? So what is this one? F union S. F union S, if I want to give you a recall, it would be probability of F plus probability of S minus probability of their intersection. Okay, there you go. So I have 1 minus probability of F is 0.3. I'm sorry, probability of F is 0.4 plus probability of S is 0.3 minus probability of their intersection. So this part in here is 0.6. So I get 1 minus 0.6, which would be 0.4. So F union S complement, which would be, which area? This area in here is basically 0.4. If I want to write this one in here, this is 0.3, and this one in here is 0.2.